If F is a homomorphism from a group G to a group H, then the kernel of F, the set of all elements that F maps to the identity in H, is actually a normal subgroup of the group G. That's what we'll prove today. You can check the description for links to relevant lessons in case you need to review any of the topics in this video, like normal subgroup, for example. To prove that the kernel of F is a normal subgroup of G, we're going to have to prove that for every element A in the kernel and every element X in G, the conjugate XAX inverse is an element of the kernel. We'll also have to prove that the kernel is a subgroup. This part is just establishing that it's normal. We'll have to prove also that it is in fact a subgroup at all. Let's get the subgroup part out of the way first. To prove that the kernel of F is a subgroup of G, we'll show that it's closed with respect to products and with respect to inverses. So we take two elements, A and B, from the kernel of F. Then, since F is a homomorphism, F of the product, AB, is equal to F of A times F of B. But since A and B come from the kernel, F of A and F of B both equal the identity. So this clearly is just the identity times the identity, which is the identity. So we see that the homomorphism maps the product AB to the identity. Thus, by definition, the product AB is an element of the kernel. So the kernel is closed with respect to products. To show the kernel is closed with respect to inverses, consider the inverse of our arbitrary element A. F of A inverse, we know, is the inverse of F of A, because homomorphisms map inverses to inverses. Link in the description to the lesson where we prove that property. Now, F of A, we know, is the identity. So F of A inverse, which equals the inverse of F of A, is the inverse of the identity. The inverse of the identity is just the identity. So we see that the image of A inverse under the homomorphism is the identity, which means that the inverse of A is in the kernel by definition. Thus, we've proven the kernel is closed with respect to products and with respect to inverses, thus proving the kernel is a subgroup of the domain group G. Now we just have to prove that it's closed with respect to conjugates, and we will have established that it is a normal subgroup. To do this, we're still working with our arbitrary kernel element A, but then we'll also need to take an arbitrary group element X, and we're going to consider F of XAX inverse. Our goal, of course, is to show that this equals the identity to establish that this conjugate XAX inverse is in the kernel. So, since F is a homomorphism, F of XAX inverse is equal to F of X times F of A times F of X inverse. We know that homomorphisms map inverses to inverses, like I said previously, so F of X inverse is just the inverse of F of X. And F of A, since A is in the kernel, is just the identity. So we don't even need to write F of A. It's not doing anything. It's just the identity. So this is equal to F of X times the inverse of F of X, which of course, by definition of inverse, is equal to the identity. Therefore, this conjugate element, XAX inverse, is in the kernel because its image under the homomorphism is the identity. And that completes the proof. If we have a homomorphism, F, from a group G to a group H, the kernel of F will always be a normal subgroup of that domain group G. Let me know in the comments if you have any questions, and check out my abstract algebra and abstract algebra exercises playlists for more. Links in the description. Thanks for watching. Persistence, couldn't even open myself up for an instant. What's the law? It's regular, I regulate my integrity, I'm a secular.